Sequence number ordering. Although causality is an important theoretical concept, actually keeping track of all causal dependencies can become impractical. In many applications, clients read lots of data before writing something, and then it is not clear whether the write is causally dependent on all or only some of those prior reads. Explicitly tracking all the data that has been read would mean a large overhead. However, there is a better way. We can use sequence numbers or timestamps to order events. A timestamp need not come from a time-of-day clock or physical clock, which have many problems, as discussed in Unreliable Clocks on page 287. It can instead come from a logical clock, which is an algorithm to generate a sequence of numbers to identify operations, typically using counters that are incremented for every operation. Roman 7. A total order that is inconsistent with causality is easy to create, but not very useful. For example, you can generate a random UUID for each operation, and compare UUIDs lexicographically to define the total ordering of operations. This is a valid total order, but the random UUIDs tell you nothing about which operation actually happened first, or whether the operations were concurrent. Such sequence numbers or timestamps are compact, only a few bytes in size, and they provide a total order, that is, every operation has a unique sequence number, and you can always compare two sequence numbers to determine which is greater, i.e. which operation happened later. In particular, we can create sequence numbers in a total order that is consistent with causality. Roman 7. We promise that if operation A causally happened before B, then A occurs before B in the total order. A has a lower sequence number than B. Concurrent operations may be ordered arbitrarily. Such a total order captures all the causality information, but also imposes more ordering than strictly required by causality. In a database with single-leader replication, see leaders and followers on page 152. The replication log defines a total order of write operations that is consistent with causality. The leader can simply increment a counter for each operation, and thus assign a monotonically increasing sequence number to each operation in the replication log. If a follower applies the writes in the order they appear in the replication log, the state of the follower is always causally consistent even if it is lagging behind the leader. If there is not a single leader, perhaps because you are using a multi-leader or leaderless database, or because the database is partitioned, it is less clear how to generate sequence numbers for operations. Various methods are used in practice. Each node can generate its own independent set of sequence numbers. For example, if you have two nodes, one node can generate only odd numbers and the other only even numbers. In general, you could reserve some bits in the binary representation of the sequence number to contain a unique node identifier, and this would ensure that two different nodes can never generate the same sequence number. You can attach a timestamp from a time-of-day clock, physical clock, to each operation. Such timestamps are not sequential, but if they have sufficiently high resolution, they might be sufficient to totally order operations. This fact is used in the last write wins conflict resolution method. See timestamps for ordering events on page 291. You can pre-allocate blocks of sequence numbers. For example, Node A might claim the block of sequence numbers from 1 to 1000, and Node B might claim. It is possible to make physical clock timestamps consistent with causality in synchronized clocks for global snapshots. On page 294 we discussed Google Spanner, which estimates the expected clock skew and waits out the uncertainty interval before committing a write. This method ensures that a causally later transaction is given a greater timestamp. However, most clocks cannot provide the required uncertainty metric, the block from 1001 to 2000. Then each node can independently assign sequence numbers from its block, and allocate a new block when its supply of sequence numbers begins to run low. These three options all perform better and are more scalable than pushing all operations through a single leader that increments a counter. They generate a unique, approximately increasing sequence number for each operation. However, they all have a problem. The sequence numbers they generate are not consistent with causality. The causality problems occur because these sequence number generators do not correctly capture the ordering of operations across different nodes. Each node may process a different number of operations per second. Thus, if one node generates even numbers and the other generates odd numbers, the counter for even numbers may lag behind the counter for odd numbers, or vice versa. If you have an odd-numbered operation and an even-numbered operation, you cannot accurately tell which one causally happened first. Timestamps from physical clocks are subject to clock skew, which can make them inconsistent with causality. For example, see Figure 8-3, which shows a scenario in which an operation, that happened causally later was actually assigned a lower timestamp. Row in 8. In the case of the block allocator, one operation may be given a sequence number in the range from 1001 to 2000, and a causally later operation may be given a number in the range from 1 to 1000. Here, again, the sequence number is inconsistent with causality. Lamport timestamps. Although the three sequence number generators just described are inconsistent with causality, there is actually a simple method for generating sequence numbers that is consistent with causality. It is called a Lamport timestamp, proposed in 1978 by Leslie Lamport, in what is now one of the most cited papers in the field of distributed systems. The use of Lamport timestamps is illustrated in Figure 9-8. Each node has a unique identifier, and each node keeps a counter of the number of operations it has processed. The Lamport timestamp is then simply a pair of counter, node ID. Two nodes may sometimes have the same counter value, but by including the node ID in the timestamp, each timestamp is made unique. Figure 9-8. Lamport timestamps provide a total ordering consistent with causality. A Lamport timestamp bears no relationship to a physical time of day clock, but it provides total ordering. If you have two timestamps, the one with a greater counter value is the greater timestamp. If the counter values are the same, the one with the greater node ID is the greater timestamp. So far, this description is essentially the same as the even/odd counters described in the last section. The key idea about Lamport timestamps, which makes them consistent with causality, is the following. Every node and every client keeps track of the maximum counter value it has seen so far, and includes that maximum on every request. When a node receives a request or response with a maximum counter value greater than its own counter value, it immediately increases its own counter to that maximum. This is shown in Figure 9-8, where client receives a counter value of 5 from node 2, and then sends that maximum of 5 to node 1. At that time, node 1 counter was only 1, but it was immediately moved forward to 5, so the next operation had an incremented counter value of 6. As long as the maximum counter value is carried along with every operation, this scheme ensures that the ordering from the Lamport timestamps is consistent with causality, because every causal dependency results in increased timestamp. Lamport timestamps are sometimes confused with version vectors, which we saw in detecting concurrent writes on page 184. Although there are some similarities, they have a different purpose. Version vectors can distinguish whether two operations are concurrent or whether one is causally dependent on the other, whereas Lamport timestamps always enforce a total ordering. From the total ordering of Lamport timestamps, you cannot tell whether two operations are concurrent or whether they are causally dependent. The advantage of Lamport timestamps over version vectors is that they are more compact. Although Lamport timestamps define a total order of operations that is consistent with causality, they are not quite sufficient to solve many common problems in distributed systems. For example, consider a system that needs to ensure that a username uniquely identifies a user account. If two users concurrently try to create an account with the same username, one of the two should succeed and the other should fail. We touched on this problem previously in the leader and the lock on page 301. At first glance, it seems as though a total ordering of operations, for example using Lamport timestamps, should be sufficient to solve this problem. If two accounts with the same username are created, pick the one with the lower timestamp as the winner, the one who grabbed the username first, and let the one with the greater timestamp fail. Since timestamps are totally ordered, this comparison is always valid. This approach works for determining the winner after the fact. Once you have collected all the username creation operations in the system, you can compare their timestamps. However, it is not sufficient when a node has just received a request from a user to create a username, and needs to decide right now whether the request should succeed or fail. At that moment, the node does not know whether another node is concurrently in the process of creating an account with the same username, and what timestamp that other node may assign to the operation. In order to be sure that no other node is in the process of concurrently creating an account with the same username and a lower timestamp, you would have to check with every other node to see what it is doing. If one of the other nodes has failed or cannot be reached due to a network problem, this system would grind to a halt. This is not the kind of fault-tolerant system that we need. The problem here is that the total order of operations only emerges after you have collected all of the operations. If another node has generated some operations, but you don't yet know what they are, you cannot construct the final ordering of operations. The unknown operations from the other node may need to be inserted at various positions in the total order. To conclude, in order to implement something like a uniqueness constraint for usernames, It's not sufficient to have a total ordering of operations, you also need to know when that order is finalized. If you have an operation to create a username, and you are sure that no other node can insert a claim for the same username ahead of your operation in the total order, then you can safely declare the operation successful. Roman 9. The term atomic broadcast is traditional, but it is very confusing as it's inconsistent with other uses of the word atomic. It has nothing to do with atomicity in ACID transactions and is only indirectly related to atomic operations in the sense of multi-threaded programming or atomic registers linearizable storage. The term total order multicast is another synonym. This idea of knowing when your total order is finalized is captured in the topic of total order broadcast.